Hello there, this is Truth Socrates. Welcome to video number 29 for my series for multivariable calculus. This is known as Math 5C at Pasadena City College. So today we're going to take a little break from all of our integration and we're going to talk about what is called the multivariable chain rule. So of course in single variable calculus, we know about the chain rule. If you have two functions, one of them composed inside the other, then the chain rule tells us how to take the derivative of this function. So today we're going to extend that rule to functions in two or more variables. I will see you in a bit on page 232. Okay, so let's begin by reviewing the chain rule that we learned from single variable calculus. So once again, it's about a composition. So let's say that you have a variable u, which is a function of x. So let's call it g of x. And g of x is differentiable. Okay, everything has to be differentiable for the chain rule to work. Okay, and we have another variable y, which is now a different function, a function of u. Okay, where of course u is that symbol that we saw a second earlier. Okay, and of course we also want f to be a differentiable function of u. Okay, so when we substitute g of x in for u, we're going to get f evaluated at g of x. Okay, but of course that is the meaning of the composition of two functions. We can rewrite this as the composition f composed g evaluated at x. Okay, and this composition is valid as long as the range of g of x is within the domain of f of u. Okay, and that is because we are plugging in g of x into f. Okay, so we must make sure that the value of g of x is part of the domain of f of u. Okay, so chain rule says if you want the derivative of h with respect to x, the variable that it now depends on, you multiply two things. First, you take the derivative of f with respect to u, and then you plug in g of x back into u. Okay? And then you multiply that by the derivative with respect to x of g of x. Okay? So what we sometimes say in calculus is that you take the derivative of the outer function, which is f, plug in the inner function, and then multiply by the derivative of the inner function. Okay? So another way to say this, maybe in a slightly simpler way, is to write this first factor as the derivative with respect to u of f evaluated at g of x. Okay? Now the problem with this notation is that you might think, okay, I'm going to take this whole thing, I'm going to differentiate with respect to u. Now wait a minute, there is no u here anymore. Okay, so the symbol unfortunately has a limitation. Okay, but we will take it to mean exactly this symbol. You take the derivative of f with respect to u, and then you plug in g of x. Okay, so that will just spare us this little detail of plugging in g of x into u. Okay, so now we are going to take a look at the generalization to this, of this chain rule involving two or more variables. All right, so what I'm going to do is I'm going to motivate the chain rule before actually telling you what the chain rule is. Okay, so we're going to use this example. You have a simple function in two variables, f of x, y. It's just one term, but of course it has both x and y in it. Okay, so let's say it's 7x squared y cubed. Okay, simple enough. Yet just ever so slightly complicated with the square and the cube. Okay, so what are we going to do? We're going to make x and y both depend on a third variable t. Okay, a single third variable. So x will be 5t plus 2 and y will be t squared minus 3. Okay, now remember the chain rule is about a composition. You replace x, y with something, we'll replace it with these expressions. Okay, so 7x squared y cubed becomes 7 times 5t plus 2 squared times t squared minus 3 cubed. Okay, find and replace, literally. Okay, so when we do that, we now get another function, a function that depends only on t. Okay, so we will give it a name. We will call it h of t. Okay, and now we're back in single variable calculus. There's only one variable there, t. Does that look like a differentiable function to you? Of course it does. And you could probably have found this derivative after just 3 weeks or so of calculus. Okay, so let's find the derivative. We will need a combination of, the constant multiple, easy enough, power rule, and of course the chain rule. Aha. Oh, and the product rule. Don't forget the product rule. Okay, so let's break it down. So what is the derivative of this thing? Well, the product rule controls the process basically. So we have 7 constant, okay? Let's take the derivative of this first factor. So the 2 goes down. The 5t plus 2, the power drops down to 1. And then don't forget the chain rule now says you have to go inside and take the derivative of 5t plus 2. That's your 5. Okay? Don't do anything with the other factor. Just write it down as a product. Okay. So that's for the first term in the product rule. Second term, you still have the 7. This time, don't do anything to 5t plus 2 squared. Leave it alone, but you have to write it down. Now take the derivative of the second factor. Okay, so drop down the 3, and then the t squared minus 3, the power becomes 2. Okay, and then chain rule says you have to go inside and take the derivative of t squared minus 3. You have times 2t. Okay, so you could have done this in basic calculus, okay? And your teacher probably would say, keep it factored, or write your answer down in as much a factored form as possible. That's what I would have instructed my students to do, okay? But that's not what we're going to do today, okay? What we're going to do is we're going to motivate this example to write down the chain rule, okay? And express it in terms of partial derivatives. Okay, I was hiding it. Okay, so let's go on to the next page. Okay, so our function is this 7x squared y cubed. So on the next page, what are the partial derivatives? Okay, so partial with respect to x, we'll get 14x y cubed. That's a constant. And then for partial with respect to y, you'll get 21x squared y squared. Okay, so let's move on down. Aha, so there they are. 14x y cubed and 21x squared y squared. Okay, but let me scoot on down the page because I do have the answer that we have from the previous page. Oh, there it is. Okay, it was right there after all. Okay, so let's take a look at what we have in this first term. Okay, do we see anything that looks like 14xy cubed? Okay, well, there's a 14, and I think this is the x, and this is the y cubed. Okay, well, that's good. It's almost all there, except there's a 5. Okay, well, where did that 5 come from? It came from inside, right? From the basic chain rule. Okay, so that was the derivative of 5t plus 2, which is the derivative of x with respect to t, of course. Okay, what about the 21x squared y squared? Yeah, there's a 21 right there. That's the x squared, and that's the y squared. Oh, and then there's the extra 2t. Okay, there's an extra 5. Now there's an extra 2t. Okay, well, that 2t came from the derivative of t squared minus 3. Okay, so in the answer that we got, it is hiding a partial derivative, 14xy cubed, in the first term, and 21x squared y squared in the second term. Partial of f with respect to x, partial of f with respect to y. Okay, so I do believe we are now ready to write down the preliminary version of the chain rule in 2 variables. Oh, look, we will upgrade it to 3 variables because, of course, if it works for 3, it also works for 2. Okay, so we have a function f in 3 variables, and let's assume, of course, that we can find all the partial derivatives of f, and we want them to be continuous. Okay, so let's also stipulate that x, y, and z are all differentiable functions of a single variable t. Okay, so we will create the composition h of t, which will be f evaluated at x of t, y of t, and z of t. Okay, so just like what we did earlier, except now we'll allow for 3 variables. Okay, so what does the chain rule say? The derivative of h with respect to t, because there's only one variable appearing here, it's the ordinary derivative of h with respect to t, just like what we did. Okay, it is made of 3 terms. One term plus a second term plus a third term. Okay? Each term basically has 2 factors. One of them is a partial derivative. Take the partial of f with respect to x. Plug in all the substitutions, x of t, y of t, and z of t. Multiply that by the derivative of x of t with respect to t. Okay? Repeat for y, partial of f with respect to y. Multiply by dy by dt. Repeat for z, partial of f with respect to z. Multiply by dz by dt. Okay? Take all 3 products, add them all together. That is the derivative of this function with respect to t. Okay, so this is a preliminary version because we're going to show you a more compact, shorter version on the next page. Okay, so to create that compact notation, okay, a sum of 3 things, and each of those things is a product of 2 things. Okay, well, that's exactly how a dot product works, right? u1 v1 plus u2 v2 plus u3 v3. Okay, so how are we going to create these 2 vectors to form a dot product? Well, it's natural to put the 3 partial derivatives together and the 3 ordinary derivatives together. Okay, so this is shorter, and that looks like x prime, y prime, z prime, doesn't it? Oh yeah. And that's exactly r prime of t, if we put those 3 functions into a single vector. Okay, so we're back to parametrizing a curve. Ooh, so that's what's going on. Okay, what about these partial derivatives? I hope you remember 2 videos ago, not 2 vectors ago. Sheesh, national video vector. Okay, what's going on today? You put the partial derivatives together in a single vector, you have what is called the gradient vector from 2 videos ago. Okay, so now the derivative that we're looking for is the dot product of these 2 videos. Okay, so now we can therefore restate the multivariable chain rule in a much more elegant version. Okay, same function, x, y, and z must have continuous partial derivatives for all 3 variables. You now have a space curve which is found inside of the domain of your function. Okay, because remember, you have to make sure that what you're plugging in is acceptable input into your function. Okay, and that space curve is parameterized by x of t, y of t, and z of t for some interval I. Okay, you take the composition f evaluated at r of t. Okay, so remember, we've seen that symbol before, okay, when we did the integral, scalar integral, contour integral of a scalar function, okay? So another way to think about it is that h of t is the function where you restrict it to the curve C, okay? Because instead of evaluating it in all of R, you only evaluate it on C, okay? Then in this case, h of t is a differentiable function of t, and the derivative of h of t is the gradient of f evaluated at r of t, dot it with the derivative of r of t, okay? So basically, it's 3 steps, okay? Find the gradient of your f, plug in the r, and then you take the derivative of r, and then finally you take the dot product of the two. Okay, so I lied, 4 steps, okay? So let's go to our workroom and let's do an example. The example I have here is a polynomial function with some linear quadratic functions for x, y, and z. I'm going to give you a rational function, and we'll see what the partial derivative is going to be. All right, so here's our rational function. We have f of x, y, z is 2x minus 5z over 3y plus 4z. And x is t squared plus 5, y is 3t minus 1, and z is negative t minus 2, okay? And it appears twice, okay? So r of t will be the vector function where we put all 3 together, and h is the composition f evaluated at r of t, okay? We're going to do 2 things. We'll find the derivative of h with respect to t, and then we will plug in the number 2 for t, okay? So you might think, oh, well, all you have to do is plug it in. Yes and no, okay? I'm going to show you that there's a more efficient way to compute part 2 instead of using the ending of part 1. Okay, so first, you know what? Let us actually show you, well, what does h of t look like, okay? So into this function, we're going to plug in these expressions, okay? So this is x, that is our x, okay? And then we have z's. Okay, let's go to z next. So we multiply minus 5 times this, and then 4 times this. Okay, oh, we're missing y. Okay, so there we go. So y is down here. Okay, so it's not too bad. We're going to end up with a quadratic in the numerator, and I think a linear term in the denominator. Okay, so again, we know how to do that in basic calculus, right? You have the quotient rule, low d high minus high d low, square the bottom, away we go. Have you heard of that? But yeah, it will be a little bit complicated because of the square, but it's not so bad. Okay, let's see how to do this using the chain rule, the multivariable chain rule, okay? So we are going to find the gradient. What were the steps? Find the gradient of our function. Okay, so our gradient of f is going to be, okay, so we're going to find the 3 partial derivatives of our function with respect to x, y, and z. Okay, so yeah, quotient rule, low d high, high d low, and so on. So let's do partial respect to x. All right, so start with low. Okay, so here's the low, and then d high is 2 minus high. The high is this. D low, partial of the denominator with respect to x. Oh wait, there's no x there, so that's 0. And then we divide by the square of the denominator. So we'll turn that into a fraction. We take this and then we square it. Okay, so of course, the second term simply goes away. So we can copy this in here. And because that goes away, okay, this can actually simplify. Okay, so that can cancel with this. Shall we do that? Maybe not, because remember, there are three things that we're going to add together. Okay, so they might have the more complicated denominator. Okay, so let's just hold off for now. Okay, we can change our minds later. Next, we have a partial derivative with respect to y. Okay, so low d high, and oh wait, this time d high, there's no y there. Okay, so the first term disappears. So we have minus high d low. The d low will not disappear. Okay, so minus high. The d low is 3, and then square the bottom, away we go. Is that going to cancel? Nope, told you. So we're just going to keep it as is. Okay, there you go. So now for our third partial derivative. So let me copy this because I'm going to scroll down. I might lose it. Yep, just lost it. So there's our function, and we want the partial with respect to z. So fraction, we want low, which will be this. D high, -5, remember this is with respect to z, minus high, that will be this, just the numerator, minus high, d low is going to be 4, square the bottom, same bottom, and away we go. So nothing's gonna, don't just cancel that, because nothing's gonna cancel here. Okay, so we need to simplify the numerator. I think we should simplify the numerator. Okay, so let's see, there's only one x, I believe, minus 8x. Let me clear the numerator. Minus 8x, and then y, minus 15y, and then z, okay, focus, minus, so that's plus 20z, minus 20z, shocker, so that does not contain any z, okay? So that is the third component of our gradient. Okay. You know what? Okay, remember last time I showed you that scientific notebook can do vector calculus, and how many mistakes did I make? That's okay, because it canceled the 3y plus 4z. Minus 3, yep, 2x minus 5z. Ooh, so far so good. Oh, look, it did not simplify the third component. Did we do one better? Well, let's see. Compute, can you simplify? Yeah. Oh, wow, look at that. I didn't make any mistakes for a change. Okay, so that is our gradient of f with respect, that's it, the gradient of f. Okay, I paused the video so that I could do a little cleanup. Okay, it's kind of like erasing the blackboards, except it's a lot faster. So now we're going to plug in r of t into our gradient vector. Okay, so that means replace x everywhere with t squared plus 5. Okay, so x is over here and over here. Okay, and then replace y with 3t minus 1 over here and over here and over here. Okay, now I'm ignoring these two because we're just going to copy this over when we're done with a z. here is our z. So we're going to put it over here and over here. And nothing there. And over here. Okay. So let me scoot out of the way. We are just going to take all that and copy it over. Okay, so there you go. That is step 1, find the gradient. Step 2, plug in the parameterization, x, y, and z. Okay, and then you might be thinking, wouldn't it have been easier to do low D high, less high D low? And yeah, I might agree with you, but would you have done that if I put a square over there? Yeah, maybe you might say, yeah, this might be the way to go. Okay. So the next step is to get the dot product. No, not yet. Did I say dot product? No, I mean the derivative. Okay, so what are the derivatives with respect to t? So we got 2t, and then we got 3, and then we got -1. Okay, there we go. So only x prime has the t in it. Okay, so final step, now we take the dot product. Okay, we're going to take this dot with this vector. Okay, so that's why I kept the denominator. Okay, because we're going to add them all together. Okay, so I only need to take one of them, and then I will put this in parentheses, or you know what, brackets, so it looks more demarcated, multiplied by the x prime. Okay, and then take the second one and multiply by the y prime, which is 3. So we can put the 3 in front instead. Looks better there. The third one we're going to multiply by -1. So we're going to subtract. Okay, and then we'll put this last term. There you go. That's the end. Okay, you don't have to expand it. There might be some value with expanding the numerator because, you know, I think only a t squared will come out. Okay, and yeah, maybe this one could also bear some simplifying. Yeah, it's really not all that bad. Okay, so that's part 1. We want to find the derivative, this derivative when t equals 2. Okay, so imagine doing that, right? That won't be very, very, very pleasant. Okay, however, okay, as I mentioned, there is a simpler way to do it, and that is, well, let's compute the resulting x, y, and z first. Okay, knowing that t must be equal to 2. Okay, so here are our functions for x, y, and z. Okay, so let's make 2 copies. So we want x at 2. Okay, so that's 4 plus 5, that's equal to 9. T is 2, so 6 minus 1, that's equal to 5. Okay, t is 2, -2 minus 2, -4. Okay, there we go. So now we know x, y, and z. Okay, now we can plug those into our gradient. Okay, so yeah, don't you think it would have been really unpleasant if we did all of that just to plug in 2, right? Okay, because now all we have to do is plug in the 3 numbers. Okay, so x is 9. Okay, so we're going to get 9 times 2, 18. 9 times 8, 72. so minus 72. Okay, and nothing in the denominator. Okay, y is 5, so that's going to be 15. And then minus 45. Okay, and we're going to get 15s over here. Okay, so again, I'll ignore the other two denominators. They're the same. Okay, now z is minus 4. So this will be minus 16, and that's going to be minus 16. Yeah. I picked the numbers so that we get something nice in the denominator. Okay, so that's just negative 1 squared. That's just going to give us 1. Okay, but there's still one more, so minus 4, so that's going to be a plus 20. Okay, so everything gone? Yep, everything gone. So that's just going to be a positive 1. So yeah, so just so there's, instead of ripping it apart. Okay, I can extract the numerator, but we'll just leave it like that. Okay, we get whole numbers, we get integers. Okay, but now we still have to plug in the 2 into the derivative. Okay, so r prime at 2 is going to give us 4, 3, and 1, minus 1. Okay, so now we're ready for the derivative at t equals 2. Is, okay, so that's negative 1 times 2, so minus 2 times 4, we're taking the dot product. 20 minus 18 is 2, I'm sorry, 20 plus 18, I'm looking at the minus there. 38 times 3, so minus 38 times 3, and then minus 72 minus 45, so minus 72 plus 45 times negative 1, so it's going to be plus 72 plus 45. Final answer, that one. Okay, so that's definitely, I would think, a lot better than going in here and plugging in 2 everywhere. Okay, that's not going to be very, very efficient. Okay, so what's that? Ooh, 32 minutes. All right, so thank you so much for watching this video. I hope you enjoyed it. So until next time, when we are going to use the multivariable chain rule to prove a theorem regarding contour integrals, we're going to show that sometimes it is more efficient to compute the contour integral of a conservative vector field using a theorem that basically just allows us to compute endpoints. Shouldn't that sound familiar? Kind of a lot like the fundamental theorem of calculus. So until our next video, I hope you enjoy the rest of your day. Bye!